So here's your chapter 15 summation. I'm going to do this real fast, fast as I can. Okay, so I got two charges here. We'll call this guy charge 1. We'll call this guy charge 2. Coulombs Law is where the chapter begins. Coulombs Law is basically an equation for finding the force between charges. Now look, charges can either attract. When do charges attract? If they're opposite. Or charges can repel if they're the same, like plus and plus or minus and minus. So here we have a positive charge and a negative charge. These charges will attract each other like this. And then let's say they're separated by a distance r, like that. We can calculate the force of attraction between these two charges. And by the way, are these two forces the same or different? We got a big negative and a little positive. Same, even though one is big and the other one's small, they're the same. The equation for finding the force between charges, K Q1 Q2 over R squared. Okay. Now, why is Q absolute valued? Kids always ask that. Why are those charges absolute valued? Well, what is plus and minus in physics? Direction. Will the equation tell you the direction of the force? Nope. You got to look at the situation. You got to look at the diagram to figure out the direction, okay? So when it comes to plugging into these equations, just absolute value the charges. All right, now when does Coulombs law become trickier? Well, when you have to do vector stuff. So for example, say you have like positive charge, negative charge, positive charge, something like this. So we'll say charge 1, charge 2, charge 3, and say that the question wants you to find the total force on charge 3 on this guy. Find the total force on charge 3, and of course you'd be given the distances and you'd be given the charges. But how would you go about doing this? Well, first thing, you got to do a free body diagram that shows the forces. So if we're focusing on charge 3, what is charge 1 doing to charge 3? Attracting or repelling? Repelling. So that's going to be, you would label this force here F31. The force on 3 by 1. Okay? Now what's charge 2 doing to charge 3? Attracting it. So I'd label that F32. The force on 3 by 2. Okay, so then what you got to do? You got to use Coulombs law. KQQ over R squared. Look, you'd have to find this distance there. Right? That's the distance between charge 2 and charge 3. But once you know what these forces are, once you've solved for them, the rest of the problem is the beginning of the whole year, right? The rest of the problem is vector. You got to find total x, total y, put them tip to tail, do Pythagorean theorem. You know, once you've done this calculation, you know, you're back to first semester, right? Just doing vectors. That's all it is. Simplifying those forces. Okay, so that's the start of chapter 15. So then the next thing is electric fields. So let's go here. All right, so electric fields behave just like gravitational fields. So whenever you have fields, there's going to be a big guy and a small guy. When I say big dude, what do I mean by big dude? Big dude is the creator of the field. So if you're talking about the gravitational field, that would be the Earth or whatever planet or moon it is that creates the field. Okay, so big M. Now look, if you stick a little mass in the gravitational field, so that'd be little m, would that little mass get a force from the gravitational field? Yep. There's going to be a force there. Now how would you calculate that gravitational force? That's this first equation here. The force of a gravitational field equals the mass in the field multiplied by the gravitational field, mg. One of the first equations you learned. Now in a very similar way, charges have what we call electric fields. So this is going to be our big dude. The big dude is the creator of the field. If you put, hey, put your phone away. If you put a little guy, a little positive charge in this field, would that little positive guy get a force? Yep, and that'd be the force of the electric field. The equation for the force of an electric field, notice that these two equations here are the same thing. M becomes Q. Because do electric fields care about mass? No, they care about charge. G becomes E. So it's the same thing. It even sounds alike. Mg, QE. It's a good song, dude. All right. Mg, QE. Now, we're almost done. If you travel a distance r from the Earth, you can find the gravitational field, right? How do you find what gravity is at a distance from the Earth or any planet? Well, it's this equation. We did this first semester. Big G m over r squared, where that m is the big dude. Now, for a charge, if you go a distance r from a big charge, you can find the electric field. Notice that these two equations are basically the same. G becomes K. M becomes Q. It's the same exact thing. You can find the electric field. Now, what's more tricky? What's trickier? Gravity or charges? Charges are trickier because are there two types of masses? Do you ever have to wonder which way objects will move in the gravitational field? No. But with charges, there's two types of charges. There's positive and negative. So look, so we got this electric field going into the big negative. If you stick a little positive guy right here, which way does the positive guy want to go when he's next to a big negative? The positive guy wants to go that way. Which way would a little negative guy want to go? The other way, which presents a problem. So it's already been figured out for us. We will define the direction of the electric field as being the direction that a little positive wants to go. So look, big positive, big negative. The direction of the electric field is always the direction that a little positive guy wants to go. So if you stick a little positive guy right here, which way does that little positive guy want to go? Away. That's the direction of the electric field. What if you put a positive guy here? Then he wants to go that way. Electric field. What if you put a positive guy there? That way. That way. That way. So what can we say about big positive? Big positive, the electric field goes out. Because why? Little positive goes that way. Now how about if you're talking about a big negative? If you're talking about a big negative, which way does a little positive guy go for a big negative? In. So in general, we can say that electric fields go out from big positive in to big negative, right? Which way do little positives want to move? I'm basically saying the same thing a different way now. Which way do little positive guys want to move? With the field. Which way do little negatives want to move? Against the field. Very important. Little positives go with the field, because that's how we define the field. And then little negatives go opposite the field. Guys, you now know everything for chapter 15. Now, let's look at a problem.